Bismillahir Rahmanir Rahim. Ospf, open shortest path first. Ospf is also an intra-domain routing protocol, just like RIP. But in RIP, we had the restriction of 15 hops in the diameter. We don't have that restriction in Ospf. And in Ospf, we look at the costs associated with reaching a network. In RIP, we looked at hops, right? We looked at the number of hops. We didn't really bother about the costs. However, in Ospf, we look at the costs. So for example, from going from R1 to N4, the cost would be 5 plus 3 plus 4, which is 12. In RIP, we said it was hops. It was 3 hops, but in Ospf, we're looking at the costs. Going from R2 to N4, it is 7. And going from R3 to N4, it is 4. So in this manner, we have different costs calculated from each router to reach a designated network. Now, making the routing tables or the forwarding tables for Ospf, they are quite similar to how we did with RIP, but instead of the hops, we are now putting in the values for the costs instead. So for R1, you have N1. There's no next router, it's directly connected to R1, and the cost of reaching this network is 4. N2, same thing, directly connected, and the cost is 5. N3, the next router we have to go through in order to reach N3 from R1 is R2. So we've put here R2, and the cost is now 5 plus 3, which is 8. To reach N4, we still have to go through R2, so that this is still our next hop. So we put here R2 as the next router, and we say the cost is 5 plus 3 plus 4, which is 12. We've made similar routing tables for R2 and R3. Now we're looking at the different types of areas in an autonomous system. As I mentioned earlier, an autonomous system is an independent system that can run on its own. So in our example, our university network would be considered as an autonomous system. So our university has different campuses. All these campuses could form areas within the autonomous system of our university. Each area is connected to other areas through the area border router. Now, the area border router will exchange information with routers within the area and find out what's going on in terms of the routing and forwarding in its own area. Each area border router will have that information about its own area. You have an area which is called Area 0, which is designated as the backbone. Okay, and this is important because as you can see, Area 0 is actually linking the other areas. All the other areas are being linked to the Area 0, which is the backbone. The information from these area border routers will be exchanged with the backbone routers in Area 0, and then eventually exchanged within the backbone routers, right? And then with the backbone and area border routers. So in this way, Area 1's border router will come to know about Area 2's border router forwarding tables. And the information will be disseminated among different routers. So eventually, all the routers within the autonomous system become aware of each other. You also have a boundary router sitting there called as the autonomous system boundary router. And this boundary router is the link to other boundary routers from other autonomous system. So we have our university's autonomous system. We also have the autonomous system of other universities, right? So you could have another autonomous system sitting here, and you could have an autonomous system boundary router, and these two routers are connected to each other. And eventually, when they exchange information with each other, this router comes to know everything about the autonomous system on the other side. So in this way, we implement the hierarchical routing, and we get to know about all the other routers. Now, to carry on with this exchange of information, we have 5 different types of packets. 5 types of link state packets. Based on what router it is, based on what type of an area it is, okay, we will have all these different types of LSPs that are exchanged. Now let's look at these different types of LSPs. The first one that we have here is considering what type of a link is there with the router. Okay, what type of a link is it? So we have 3 different types of links: transient link, stub link, and point-to-point link. In this case, this is the point-to-point link. The 2 routers are connected directly to each other using a point-to-point link. You also have something called a stub link. Now this network is kind of like at the end. Okay, so information in this network, you could either have information going to it, or you could have information coming from it, but you would not have information going through it. Okay, that's not possible. So the stub is either the source or the sink, but it cannot be a path to another place. An example of a stub link would be your home network. So in your home network, you're either generating the information to send it out to others, or you are syncing in the information. Basically, you're taking the information, okay, right? You're the destination. But you don't have your network, your home network, being connected to other devices. This is what we mean by, so this link is this stub link. And then we have a transient link. Okay, in a transient link, you're actually connected to other routers in here. Okay, so in reality, how is this? It's not like this. In reality, it is something like this. Okay, so you have this network and you have this connection system in the middle like this. So from this router to this router is 1 hop. From this router to this router, 1 hop. This router to this router, 1 hop. So any link, anyhow you try to communicate, it's still 1 hop. Similarly, from here to here, 1 hop. Okay, so this is your transient link. And when you have a scenario like this, it's called a transient link. So this is the first type based on the types of router links that we have. The next one we have is for a designated router. Now, what is a designated router? This is a network, right? But this network is somewhere in the middle, and it's connected to routers R1, R2, and R3. Now, the question is, which of these routers will do the advertising for this network? Okay, you can't have all 3 routers doing the advertising. It will generate too much unnecessary traffic. Instead, we decide upon one router and give this router the role of a designated router. Okay, so the advertiser network as a node. In this case, you're advertising this network as a node. One of the routers is assigned as a designated router and does the advertising. So in this case, if I assign a higher priority to R3 and make it a designated router, R3 will be responsible to advertise this node and the address of these routers connected to it, right? So R3 will do the advertising. However, because different networks or routers could connect to these routers from different places, R3 will only advertise the addresses and not the cost. Okay, and not the cost, because the cost of reaching R1 could be different from another place. So this is another type of LSP, which is the network based on the network link. And then we have an LSP that is exchanged between an area, a router sitting at the boundary, okay, the area border router. So this router has got information about the area, and it also has links with area 0. And this router is responsible for exchanging the information from here to here and from here to here. Okay, so this is done by the area border router. It advertises the summary of the links collected by the backbone to an area, or it advertises the summary of the links from the area to the backbone. So this is a summary link to the network. So this is the third type of LSP that we will need. We also have, as we saw last time, we have an autonomous system boundary router that is responsible to exchange information with other autonomous systems. So you've got the information flowing from here to here and from here to here, exchanged, right? So this is another type of LSP required for this. And then we've got an autonomous system router announcing the existence of a single network outside the AS to the backbone area. So in this case, to take an example, if the area 0 was belonging to STC, then our home network, right, our home network would be announced by the AS router to area 0. So area 0, the routers in area 0 come to know about the existence of our network through the AS router. And this is called the LSP for the external link. So in this way, we have 5 different LSPs that are implemented in Ospf. Now we have different message formats for Ospf based on the 5 different LSPs that we can make. So what you're seeing first in here is the common Ospf header. You have the version. The type here will tell you whether it is a type 1 or 2 or 3 or 4 or 5. You have the message length. You have the source router IP address, who has generated this packet. You have the area ID. Then you have checksum, authentication type, which is, are you using a password? Are you using a simple authentication method, or are you using MD5? Okay, it will be covered using the authentication type. And then you've got other information, the actual authentication related information in here. So this is the common Ospf header. All LSP packets will have this by default. Now we're looking at the first type of packet, which is the hello packet. This is exchanged by the router after it comes up, right? After it comes up, it's going to make a note of its neighbors, the direct neighbors, and then it'll exchange the hello packet with the other routers. So you have the Ospf common header with the type given as 1. You have the network mask for the router given here. You have the hello interval, which tells you after how many seconds will the router send this packet again. You have priority. If the priority is set higher in here, it means that the router is a designated router. Okay, so this router is a designated router. And then you have a dead interval, which means how long do you wait for an update from another router before assuming that the router is down. Hello interval and dead interval, these two fields are the same for all routers within a given network. They will all have the same hello interval and dead interval. If you do have a designated router, you give the IP address in here. And if there's a backup designated router, you give it here. Now, this field that we see here, this will be repeated for all the entries in the forwarding table for this router. Then we have a packet, an LSP for database description. So the type here will be 2. You have the message sequence number, which is telling you how fresh the message is. And we have the link state general header, which is going to give us the information about all the packets. Okay, and if you want to see the link state general header, this is the link state general header. So it'll tell you the link state age, type, okay, and the type is here given: router link, network link, summary link, or AS external link. So it'll tell us the type. It'll tell us the link state ID of that, the information that we are requesting. It'll tell you which router is advertising the details of this link state, the sequence number, and the checksum and the length. And this link state general header, this is going to be repeated in here, okay, for all the entries in the network. So you would have a lot of entries in the database description packet. Because remember, the database description is really like the master copy of all the links and the connections in the network. Okay, so this is why you're having the link state general header placed in here. And we saw this in greater detail in the lab. We saw this in the OSPF lab, how we had all these different packets interacting with each other. So that's the link state general header. You have type 4 packet, which is the LS request, if I'm correct. So you've got, let me just confirm it. Type 1 is hello. Type 2 is database description. Type 3 would be LS request. Type 4 would be response. And type 5 would be acknowledgement. That's right. So yes, indeed. So this is, you have the link state update. So we haven't shown the link state request packet. You've seen that in the lab, right? Instead, now we're looking at the link state update. So what happens is you have two routers sitting here. Okay, let's say R1 and R2. Now R2 sent to R1 the database description. Okay, all the database description. R1 saw this description and realized that there were some entries that it did not have. It did not know about some entries in the database. So R1 will now send a link state request packet to R2, asking it for the specific entries that it doesn't have. It will not ask it for all the information. It'll be too much. It will only ask for the information that it does not have. So in response to the LS request, R2 will then send an LS update, right? An LS update. So this is the LS update. The number of link state advertisements it has included in it. So if R1 requested for 3 updates, it's going to say here 3. Then you have the link state general header, okay, which is this. It's going to give all the information about it. And you have the link state advertisement, okay? And this will be additional information about that particular link state that we have seen. So after receiving the link state update successfully, R1 will then generate a link state acknowledgement, okay, an acknowledgement saying, confirming that it has received the update successfully. So you have in here the header type, which is 5. You have the link state general header. And in this case, so by placing this information, and as you know, there will be a list of this. It's not just one. So you've got plus, plus, plus. Okay, you've got a list in there. And this is really showing you that I have received all this successfully from R2. Now I have given you this additional information that you could see about the details. So Ospf implements the link state algorithm after each router has created the shortest path tree, as we saw in link state. The algorithm then needs to use it to create the corresponding routing tables, okay, or algorithm. And then the algorithm needs to be augmented to handle sending and receiving all 5 types of messages. So in Ospf, along with the basic link state algorithm, we are also dealing with sending and receiving these 5 different types of LSP messages. So this was the functioning of the Ospf routing protocol.